So we have our first problem set due, and to remind you, it's due in your PA's mailbox at 3 o'clock, and then everyone can go over to closing. And the fun just keeps rolling. There'll be another problem set coming after that. All right. Okie dokie. So last time we were laying down these foundations for electrostatics. So this is looking at the problem when we have charges that are fixed in space. And Coulomb's law is the foundation there. And from that, we define the electric field in electrostatics in terms of the source from all the individual charges producing the 1 over r squared central force, or and from the principle of superposition, we can think about that in terms of a sum over the discrete charges, or more generally thinking about it as an integral over the charge distribution, the charge density. And although this is formally correct, we rarely actually use this particular form because it's a messy thing. We'll talk about it. I mean, these are vectors, so we have to integrate vectors, and we have to think about all the different components and integrate them independently. And so generally, that's a very messy thing to do and not particularly useful unless we have some symmetry relations like we discussed last lecture, thinking about atom symmetry or something like that. So we want some more general expressions that are more generally useful. And to remind you, so this formal solution derives from what are Maxwell equations for electrostatics, or the field equations. And to define our field, we need to define the curl and the divergence. As you see in your homework assignment, if you know the curl and the divergence of the field, then you have a formal expression for the field. Helmholtz equation, the Helmholtz theorem, tells us that any field is defined by its curl and its divergence, okay, over all space. So what we reminded ourselves of last lecture was Gauss's law. Gauss's law is the law relating to the divergence of the field, which, based on the divergence theorem, can be related to the flux through a closed surface. And that flux then is equal to 4 pi, for 4 pi steradians, times the charge enclosed in the volume bounded by the surface. Everyone remembers that. Now, Gauss's law is always true, but it's not always useful as a way of determining what the electric field actually is. I mean, it's a rookie mistake to always say, when I want to find the electric field, just pull out Gauss's law, because you do that, you know, in your freshman E&M all the time. And when we can use it to find the electric field, it's the best thing in the world to do. You should do it. I mean, you should not do this. This would be super crazy. But just because Gauss's law is true doesn't mean we can use it to immediately determine what the electric field is. So the question is, when can you and should you use Gauss's law to determine what the electric field is? Yeah?
when you have a symmetric
So, exactly. So the key is Gauss's law is killer when we have symmetry. Okay? And what we mean by that is that if the symmetry tells us the form of E such that E is constant, or I should say the E dot normal to the surface is constant, then the flux integral is such that I can pull this out of the integral when I think about constant on a surface. Excuse me. Not constant everywhere, but it's constant on the surface. Then I can pull this out of the integral, and then this becomes E dot n hat times the surface area, and that's then equal to whatever the enclosed charge is. So one should use Gauss's law to get the field when this is true. If it's not true, well, then it's not going to be so useful for determining what the field is. Okay? So let's remind ourselves of some of those very simple examples. So if I have a spherically symmetric charge distribution, of some kind. I'm not saying necessarily that it's uniform, but what I know in this case, I'm saying, what I mean by spherically symmetric is that rho as a function of x only depends on the distance from the origin, putting the origin at the center of the charge distribution. It may vary as a function of r, but it's independent of theta and phi. Okay? So, when that is true, we know the form of the electric field immediately from symmetry. We know, first of all, that the magnitude of E can only depend on r. It cannot depend on theta and phi, because how would it know where I am in theta and phi? It's spherically symmetric. It can't possibly depend on that. Moreover, we know that the fields extend away from the charges, so it must also be in the E sub r direction. So immediately from symmetry, we know that. And thus, we know what kind of surface we should choose in order to determine the flux integral. We should pick up a surface whose normal is in the radial direction. So we should choose a sphere as our Gaussian surface. Whose normal is in the radial direction, in which case E dot n hat is E sub r, and if that's the radius of the sphere, if we call the radius of the sphere r, then the flux integral E dot n hat dA, well, the electric field is constant. Its magnitude is the same everywhere on the surface of the sphere, and thus can be pulled out of the integral. And that integral is the surface area of the sphere, 4 pi r squared, which is equal to the enclosed charge at that radius times 4 pi. And thus, the electric field is the enclosed charge at that radius over r squared. And that's the whole story. Familiar from your freshman physics. Similarly, if we have a cylindrically symmetric rho, so we have some kind of charge distribution that has a cylindrical symmetry. And in this case, what we really want, in order to do this problem exactly, it needs to be infinitely long in the axial direction, which we'll call z, so that what I mean by cylindrical symmetry is that rho is a function. I mean, if I call the cylindrical coordinates, and this is always annoying, what do we call the cylindrical r?
S.
S? You like S? That's fine with me. I never know what to call it, because we got rho, we got r, I always call it squiggly rho. We'll do S. That's a good one. So it only depends on S. So generally, cylindrical coordinates, we would have S, phi, and z. But for cylindrical symmetry, what I mean is it only depends on this cylindrical distance from the axis. If we didn't have infinite length, then of course the charge density would depend also on z. Because it would be something like this z and then 0 outside that z. So under the case that I have exact cylindrical symmetry, again, we know the form of the electric field. It has to firstly, its magnitude can only depend on this radial distance s. How would it know where it was on phi or z? There's no marker. So it can't do that. Moreover, we know that it points away from the charge. It can't point to in the z direction one way or the other, because how would it know where it was? There's no marker along the z-axis, and it can't point one way along phi, because how would it know? So it must be in the electric field must point like that, either plus or minus, okay, depending on the sign of the charge. So again, the natural thing to do is to use Gauss's law with the Gaussian surface such that the electric field dotted onto this is something which can be factored out of the integral. And thus what one would do is take well, I can put the cylinder wherever I like, let's put it inside the charge. It doesn't really matter. So now I'm going to take I have to have a finite volume and surface, so here it is. And the electric field points in the cylindrical radial direction. And thus, if this has a radius s and a length L, then the flux integral over this is what? Well, E along the end caps of the little cylinder here, E dot n hat is 0. So there's no contribution to the flux on the end caps, and all the flux goes through the label of the soup can. And so the surface area then is the surface that contributes to flux, is the surface area around this part of the cylinder, right? And that is the circumference times the length. And that is equal to 4 pi times the enclosed charge in that Gaussian surface. And thus, for the cylindrical symmetry, we have the form of the electric field is equal to lambda enclosed divided by, in this case, S times 2, where lambda is the charge per unit length. Okay. The final symmetry that's standard in thinking about Gauss's law is to think about planar symmetry. So what here we have is some kind of I can never draw perspective very well, but my very best. So the point here is that my charge distribution here depends only on Z and is independent of X and Y. It's constant, infinite charge distribution in X and Y. Okay? So in this case, again, we know instantly what the form of the electric field is. The magnitude of the electric field can only depend on Z. It cannot depend on X and Y because where the heck am I? In X and Y I have no marker, I don't know, there's nothing that distinguishes one X or Y coordinate from the other. So from that perspective, we know instantly it can only depend on Z. Moreover, the electric field direction must be in the Z direction, because how would it know to point along one direction, X or Y? Nothing would pull it in one direction relative to the other, again, for an infinite plane. So we know the form of the electric field is in electric field. The principle can vary as a function of Z and points in the Z direction. Okay? So in order to determine what the electric field is, again, we want to have a surface where the electric field dotted into that surface is either 0, so we can ignore those parts, or a constant, so that we can factor it outside the integrand. Like we did here, it was 0 on the end caps, and the dot product was constant along the soup can rate. So we make the famous pillbox. I think in the 19th century, everyone had a pillbox, so that's what they called them when Maxwell did it. But you know, do you have a pillbox? I don't really have a pillbox. If you do, I don't really want to know. Yes, yeah. So here's my famous pillbox. this is supposed to go, through the surface on the other side. So the surface is cutting through it. Okay? And if my charge density then such that the electric fields are pointing away or towards, its density is plus or minus. So there's a little cap here which has some surface area A. There's some width or height to this pillbox. And the little pillbox has area A on the bottom. Yeah, this drawing is pathetic. So, in this case, the flux integral the electric field points on the z, in the z direction, and thus there's no contribution, there's only a contribution to the end caps. There's no contribution to the azimuthal part of the pillbox. And it's independent of where I am in x and y. And because of this symmetry, it's the same on both the top and bottom of the pillbox. So this is 2 times the electric field at that radius, or at that distance, times the area is equal to 4 pi, the enclosed charge at that distance z, if I'm a distance z above the height of the plane. Okay? And so this then tells me that the electric field strength is 2 pi sigma enclosed at that z, which is sigma enclosed is the surface charge density. Okay. Of course, if I'm outside if this charge distribution had some thickness, then of course the electric field the charge enclosed varies as I'm inside that charge distribution. But once I'm outside, if the charge distribution is 0 outside, and I'm looking at the strength, then this would be, in fact, independent of z, right? Because the surface charge density enclosed would be the same no matter what z I was at, in which case this would be a constant magnitude. Yes?
So this is, I guess, kind of a random question, but is it ever possible, like if you don't have a natural symmetry, to use some sort of coordinate stuff to, like, I don't know, like if you have something that's almost symmetric, like an ellipsoid or something like that, is it ever possible to make use of Gauss's law by, like, a coordinate transform or something like that?
No, not really. I mean, Gauss, I really think Gauss's law is as a means of, let me qualify that a little bit. Gauss's law is useful as a means for determining what the electric field is when I have symmetry. Now, of course, we don't necessarily have the perfect symmetry, so then we have to have some idea of how good of an approximation it is. So one way in which we could see that is, for example, we just discussed in these 2 cases that we needed an infinitely long cylinder or an infinite plane. Now, I don't got no infinite cylinders, nor do I got no infinite planes. So what was the point of this? Well, as we know, I mean, this is always a matter of scales. So when I'm saying something is infinite, what I mean is something is really big compared to something else. So in this case, what this means is that if I'm at a distance that is small compared to the length of this cylinder, then I expect, you know, here I am, I'm right up here, I can't see the ends of this thing. So, excuse me, I can try on my nose. And so I can't see the ends, so from my perspective it's infinite. So just from symmetry, I expect that the electric field points pretty much in the radial S direction out here, and out here it's not. So that's the kind of physical thinking one should use. So Gauss's law is useful, even though it's not exact in this case, if I can approximate in some way, because of my physical reasoning, geometric reasoning, that symmetry is a pretty good symmetry, well then I would use it. We do know that. That's where we use Gauss's law in this kind of thing. There's what we would call, you know, edge effects that we can ignore. In terms of more general things like, you know, well, it's an ellipse. I mean, yeah, I got ellipsoidal coordinates. But we would have to be very careful to think about this question, whether through symmetry one can find, one can find a circumstance where we know that we can factor it out, at least approximately. It's very rare, except in these cases, which are pretty useful cases. All right. So, I'll have a little practice for this in next homework, just to remind you some things. Let's see. So, let me get my notes so I remember what we're at. I think I remember, but it's getting older. Aren't we all? All right. So, I want to note one little thing. Some people brought this up in problem session class yesterday. Let's look at the divergence theorem again, and let's look at del dot E for a point charge. Okay, so let's say we have a point charge at the origin. Doesn't matter that it's at the origin, but let's just put it there. Make this life a little easier. And let's calculate the divergence of the electric field. So the electric field in this case is Q over R squared E sub R, or equivalently that, right? All right, so Qx over R cubed. So let's take the divergence of the electric field for the point charge. Well, we have our well-honed skills now in Einstein summation rules. So the divergence is partial I e sub I, sum over I, which is partial I q, the ith component of position, over R cubed, sum over I, which is equal to Q over R cubed times partial I xi, sum over I, plus Q xi partial I of 1 over R cubed, which I'll write as magnitude of x cubed. Is everyone clear on how that all that stuff worked, right? I wrote out the divergence in terms of summation convention, and then Q is some number, but B's are position dependent, so I just take the derivative according to the derivative product rule. Okay? What is this? Well, this is the partial with respect to xi of xi, which is 1, sum over I, which is 3. Okay? What about this? Well, I have to take the derivative with respect to the ith component, right? So this is equal to xi, or I should write it xj. Don't use, you used I already, don't use it to the 3 halves, right? That's the magnitude of x cubed. So I have to take that derivative, and what I get is the magnitude of x cubed times 3, or fifth, sorry. Yeah, x I. Minus something, sorry, minus. All right, so so I got 3 times this, so let's write that out. I got 3q over r cubed minus 3q xi over x to the 5th. xi, sum over I is the magnitude of x squared. So this becomes 1 over r cubed, 0. So the divergence of the electric field associated with point charge, according to this lovely analysis, is 0. However, we know from the divergence theorem if I make this a sphere at the origin, then this is equal to 4 pi times the charge enclosed in that sphere, which is 4 pi cubed. Right? So if I put a sphere at the origin, here's my point charge. I got my fluxometer, sniffs out that flux inside the charge, and this is equal to this. And this is supposed to be equal to the integral of the divergence over the volume enclosed. So something's a little fishy here, because we just said the divergence was 0. And if I integrate 0, I should get 0, shouldn't I?
You only have a charge at 0. So you have an indeterminate form, right? You have a 0 over 0.
We do. So the issue here is, as Kyle is discussing, we have a singularity at the origin. So our calculus breaks down. Okay? So we have a singularity at the origin, and we're going to come back to that in a moment, but this divergence is not defined at the origin. It blows up because of this indeterminate form, the 0 over 0. So this divergence is actually proportional to a delta function, as we will see in just a little while. And that's an important mathematical tool we will use. Okay. We'll come back to that. So we got the divergence, we need the curl. So the curl of E, in this case, we have a central force for electrostatics. And it's quite then easy to show that the curl of E is 0. And as we see from Helmholtz theorem, this is one and the same as saying that the electric field must be thus the gradient of a scalar. And by convention, that scalar is minus phi. So this is in relation to potential energy that will remind ourselves the convention that we put this minus sign here. So phi of x is the electrostatic potential. Okay. And of course, from the the Stokes' theorem, if I have a closed curve, C, which thus bounds an oriented surface, this potato chip, and by the right-hand rule, because, most of us are righties, but I'm sorry, lefties. Well, you're better off. You can write and do the left-hand, right-hand rule at the same time. I can't. Then we have the notion of the direction of the surface, that the flux integral of the curl through that open surface bounded by the curve is equal to the circulation integral around that curve. That's, of course, Stokes' theorem. And this is thus 0 in electrostatics. Okay? What that means then, of course, is that the integral between 2 points, this of E dot EL, is independent of path, right? Because if I call this my closed curve, and this, the curve from this point to this point is L1, and from this point to this point is L2, then the circulation integral E dot dl around that curve is equal to the integral from A to B of E dot, well, I'll just write that one, L1 plus L2 from B to A, E dot dl is 0. And thus, the integral along L1 from A to B is minus from B to A, but minus from B to A is A to B. Okay, so of what we know for a irrotational field a field whose curl is 0, that the line integral is independent of path and only depends on the endpoint. And that's equivalent to saying that the electric field must thus be the gradient of a scalar field, because from the fundamental theorem of integral calculus, the integral of the directional derivative across along a path is the antiderivative evaluated at the endpoints. Okay. Right. So, so we define, as you know, define a point at which phi of x, I'll call that point ground, is 0. So the point x ground is the ground, the place where the potential, electrostatic potential, is 0. Okay? Thus, the electrostatic potential at an arbitrary point is related to the electric field by integrating along any simple path from ground to the point of interest. So for example, if we had symmetry and we could simply determine the electric field from Gauss's law, then we can also simply determine the potential by first finding the electric field from these, simple Gaussian integrals, and then doing the line integral along the symmetry direction in order to determine what the potential is. When we have symmetry, that's what we should do. However, as we were discussing, in most contexts, that's not what we got. So we can't simply determine the electric field from Gauss's law in all cases. And in fact, really often we go the other way around. That's to say, we use our field equation to determine phi, and then find the electric field, if we so desire, as minus the gradient of the electrostatic potential. So most of electrostatics is the problem of determining the potential. That's pretty much, the first 3 chapters of Jackson. So what, formally speaking, because we're going to need this formalism when we think also not just about electrostatics, but when we start talking about dynamics and radiation. So what is a formal solution for the electrostatic potential given the field equations? So we're given del dot E is equal to 4 pi rho. We want to find the solution for the electric field. How do we invert Maxwell's equations to find E generally. In what we had here was a case of symmetry, we can find it, but how do we have a more general solution to that? Well, this equation, what we just said is del cross E equals 0, is equivalent to saying that the electric field must be minus the gradient of a potential. Then we can plug this equation into here. Del dot minus rad phi. And del dot del is the Laplacian equals 4 pi rho. So, excuse me, the combination of Gauss's law and the irrotational nature of the electric field tells us that the electrostatic potential satisfies this equation, which is called Poisson equation, not Poisson's equation. Poisson. We're sophisticated. All right. So the question then is, what is the solution to this equation? So, the equation of electrostatics one and the same Poisson's equation. Which is and the solution, well, all these PDE can be expressed. The solution is the sum of a particular solution to the equation plus a homogeneous solution which satisfies the boundary conditions. So the homogeneous solution is something which satisfies del squared phi is 0. The particular solution satisfies a particular instance of this. And this is a solution where the homogeneous solution is chosen to satisfy the boundary conditions. And this equation, if we have rho is 0, is called the Laplace equation. Okay? So first, let's look at the particular solution. So, to solve for the particular solution, we're going to use the method of Green's functions. So, what do I mean by that? Well, the idea is the following. This is a linear PDE, okay? And therefore we have the principle of superposition. So if I can solve the solution for a point, then I can use delta functions in order to create the continuous distribution as a superposition of those points, and therefore find an arbitrary solution as a superposition of point charge solutions. That's the Green's function method. In electrical engineering, we call it impulse response. If you know the response to a delta function, you make up any signal as a sequence of impulses and you add them up, and that's the whole thing. So, the idea then is to the Green's function for the particular solution is the potential for a unit point charge. Okay? With no potential at boundaries. So I'm not putting conductors around or anything. There's just no, this is the only thing in the problem. So, in this case, my rho at x is a delta function located somewhere. Okay, so this is the position of point source. So the Green's function satisfies the Poisson equation. We call the Green's function G for some crazy reason I never figured out. And oh not, I guess. So that's the Green's function equation. This is the Green's function associated, finding what the Green's function given the source at x prime. It only depends on the difference because the source only depends on the difference. And we have to find the solution to that equation. And then once we have that solution, because I can always write the charge density at x as the weighting as the strength at the position of the source times the density of the source, right? That's just a trivial identity of delta functions. Then the convolution, remember convolutions? Of the Green's function with the source gives me the particular solution by linearity. Because all I'm doing is I'm saying the source is made up of a superposition of point sources. Each point source gives rise to a Green's function. I just weight the Green's function by the strength of the source at each point in the source and superpose them, and by linearity, that's the particular solution. Is that logic clear? You're just using the principle of superposition. Each point gives rise to this potential, and you just weight them by the strength of the source at that position. So if we know the Green's function, we got the particular solution. All right.
Does the Green's function depend on the shape of the boundaries?
Not it's in case of this particular solution. We could, and we often do, include a Green's function that takes into account both the particular solution and the homogeneous solution, so that I can put boundaries, find the Green's function that accounts for the boundary conditions as well.
Okay. So
But that's not what we're doing here.
when you solve the equations for the Green's function,
Uh-huh.
um,
The boundary condition is that the field goes, or the potential goes to zero at infinity. That's our boundary condition. All right, so how are we going to solve this equation? Well, that looks not particularly well defined. I mean, we got a delta function. What the heck, you know, mathematician would probably be throwing up all over the floor here when it's on that. It would be very messy. Yeah, we're cavalier. There is a well-defined meaning to this, and typically one of the ways delta functions are defined is in terms of Fourier transforms. Right? That's where they're in some sense quite useful in their definition. So the way we can easily solve for this equation, or the solution to this equation, is to use Fourier analysis. Okay? So, remember that a delta function is equal to the Fourier transform of a constant. So if I were to integrate e to the I kx over all k, that is a delta function, right? And for in 3D, I want to say this, to integral d cubed k over 2 pi to the third e to the I dot x minus x prime. Okay. All right. We want to take the Fourier transform of both sides. We'll define the Fourier transform with the tilde. The Fourier transform of the Green's function as a function of k is equal to, let's see, do I put my 2 pi's the way I want them? Who stole my notes? I know someone did. Yeah. Shove it over there. All right. Yeah. Okay. So we'll call the dummy variable here y, e to the minus I, k dot y, g of y. Okay, so g of y is e to the cubed tilde to the I k dot y. All right. So, what we need to do then is to take the Fourier transform of both sides of the equation. Okay? So, we know what the Fourier transform of the right-hand side is. That's equal to 1. And we need to take the Fourier transform of this. How do we do that? Well, let me do a little aside here. The partial with respect to x of e to the I k sub x x e to the I k x right? That's easy enough. So, what is the gradient of e to the I k dot x? Well, is the k vector on the k vector, right? Because each component will bring down ik, and we have the vector. So the Fourier dual, whenever we see the gradient, we can replace it by ik. So the Fourier transform of del squared G goes to ik dotted into ik G of k. Each del becomes ik vec, and del squared is del not del. So this tells me that minus the magnitude of k squared, g tilde of k, is equal to 4 pi.
2 pi. Oh, never mind.
Yep, that's good. Oh, I see one thing I messed up. I knew something was wrong. The Poisson equation has a minus sign. So the Green's function has a minus sign in it. The Green's equation. Yeah. So, blah, 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 minus 4 pi. So the Green's function for the Poisson equation is equal to this in Fourier space. So now we just have to take the inverse Fourier transform to find the Green's function. Okay? So the Green's function as a function of its argument is equal to the integral over 3 k vectors, g tilde of k, e to the I, k dot y. Which is equal to we got 8 over 4 over 8, 1, and then we got 1 over 2 pi squared. The integral over 3 k vectors. E to the I k dot y over the magnitude of k squared. Okay? So, that's the integral we got to do. So to do that, we can use spherical symmetry in k-space, because what we see here is that the Green's function only depends on the magnitude of k, doesn't depend on the direction of the k vector. So there's a spherical symmetry in k-space. So we have a kx, a ky, and kz that we're integrating over. But the Green's function is constant on the sphere of constant magnitude of k. All right? So to do that, we need to choose some direction to be the kz direction, or one of these directions. There's only one other vector in the problem, that's y, which is fixed. So we might as well choose the y-axis to be the polar axis here. In which case, there's an angle k for the k vector in the spherical coordinates. All right. So with that said, we have d cubed k is equal to k squared dk sine theta d theta d phi. All right, that's the volume element in k-space. And we have to integrate the function e to the I k dot y over k squared. This is equal to k y times the cosine of the angle between that as defined. So this is the magnitude of y, is the magnitude of k. All right, so the integral that we're doing here thus is the following. First of all, this integral, the function is independent of the phi variable, so we can integrate this over all 2 pi angles of phi, so 2 pi squared over dk. Moreover, and this is a trick that you often use when thinking about spherical coordinates, it's often the cosine of the angle that we care about. And remember, d cosine theta is minus sine theta d theta. So this d cosine theta we call d mu, where mu, theta goes from minus pi to pi, so mu goes from minus 1 to 1. We do, but if I go from minus 1 to 1, then I've switched the integral. So an integral d theta, d sine theta, from 0 to pi is the integral minus 1 to 1 d. Because the pi is the minus 1. Just. All right, so with that said, what do we got? Our Green's function now, we have 1 over 2 pi squared. We have the integral k dk from 0 to infinity. We have 2 pi. We got the integral mu goes from minus 1 to 1.
Is that k squared?
There is no
That's a k squared. Thank you. Thank you. And then we have e to the I k magnitude of y mu magnitude of y k divided by k squared. All right, so this cancels. And we now integrate this. We get 1 over pi. The integral k goes from 0 to infinity. The integral of this is equal to sine of k times the magnitude of y divided by k times the magnitude of y times 2. Do that integral. And doing this integral can be done, and the answer is dun 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 1 over 1. Leave that as an exercise to the reader. So, what have we found? What we found is that the Green's function for the particular solution here, the boundary conditions that the thing goes to 0 at infinity, is that the Green's function as a function of its argument is equal to 1 over its argument. Of course, we knew that, because that is the potential of a point charge at position x prime, right? We knew that. So what the heck did I just waste a half an hour for? Well, we'll see when we get into dynamics. We're not going to know it. We wanted to see the methodology we use. But what we see here is that the Laplacian of this is equal to minus 4 pi times the delta function. In fact, this resolves the paradox that we just discussed, because, of course, this is the gradient of, this implies this minus the gradient of this is equal to 4 pi times the delta function. Bring the minus sign on the other side. And what is this? Well, this is the gradient of the potential of a point charge minus the gradient, which is the electric field of a point charge. So del dot E for a point charge is not 0, except when x doesn't equal x prime. When x equals x prime, it's infinity, which was the singularity that we talked about. So there's the resolution to that paradox. Okay, so given the Green's function, we know the particular solution. The particular solution is to the Poisson equation is the potential at position x. We said we must integrate over all space, weight the Green's function by the source at the position of the source, which is thus equal to rho x prime, x minus x prime. or integral dq at x prime which of course, if I take the gradient of this, I get Coulomb's law. So typically, if we're given a charge distribution, we would not find the electric field directly by integrating all the vectors. Instead, we would integrate the charge distribution to get the potential, and then take the gradient of that to get the electric field. Now, this is assuming there's no other boundaries with some other voltages and charges on them that are not included in this particular solution. And we'll come back to that next time, just discussing that idea. All right? So this is the formal solution to Maxwell's equations for electrostatics.